We solve essentially our last problem or last method to kind of solve this problem of our kind of stress state, and this time using linear algebra in order to find essentially some of these, basically the stress state at some random orientation, 30 degrees counterclockwise, et cetera, and we're going to use essentially this linear algebra approach in order to kind of find these solutions. So let's go ahead and let's figure it out. So let's go back to Mathematica. So this is our stress tensor. So I am going to use a little bit of a different notation. I'm going to call this stress lin as in linear algebra. And we're just going to look at our sigma xx. So that's going to be sig xx, sig yy, and sig xy. So this is going to be our stress lin. Let's look at it in matrix form, which is just going to be a vector just like this. And again, we're just using this approach that we kind of outlined in the notes, where we could use this transformation matrix here, T, and actually we defined that already in our Mathematica notebook all the way at the top right here. So again, using degree mode in Mathematica, make sure to do that in order to solve this problem correctly. And so now we could go ahead and figure out that first question very, very simply, very, very directly, and just multiply. If I want to find the stress state in the new, at some random orientation, not random orientation, but some basically plane of interest, which in this problem is a 30-degree counterclockwise rotation, all I have to do is do my stress lin dot my t, actually t dot that, t dot my stress lin. I have this, and then I'm going to substitute slash dot theta. Theta goes to 30 because we're counterclockwise, so positive. I want to look at this I want to look at it in the matrix form. And this is what I get. So let's go back and look if that matches what we've kind of solved previously. So our sigma x prime is this. So again, match, match, match. Rematching, that's really, really good. Again, this is the beauty of kind of mechanics. And then let's look at it right here again. And look at here's my sigma yy right here, and my sigma xx right there. That's it. Everything's matching. But look at how much simpler this approach is for finding that this kind of orientation, this stress rate at any rotation. So you don't have to kind of think about it. And again, when problems get more complex, if I ask you, again, I could ask you at some orientation, 15 degrees from the principal stress state, you could still get some intuition. So you could combine essentially approaches in order to kind of solve this problem. So we've solved that with one line of code very, very easily, very, very simply, and very, very straightforward. So how do we find the principal stress state? Well, so we need to figure out at what orientation, what theta will I get basically only principal values here. Well, you can do that fairly straightforward and simply with Mathematica as well. So let's go ahead and do that right now. Stress state, I need to figure out when does this value, my shear stress, equal to 0. So let's go ahead and do that right now. So stress lin right here. I want to take out the third component. Oops, nope, I don't want to take out that third component. I want to do my parentheses around it. And then I want to solve for when this value is equal to 0. So solve here for this equal to 0, solve for theta, and I get my answer here. I want to look at it numerically, so I'll do this, and then here I could pull out my solution, and then this is just going to be 22.5 degrees, which matches what we've seen kind of previously with more circle approach, and then again with our other approach as well. Now you might be asking about some of these other values here, and all it is we're just basically, again, circular symmetry and angles and circular symmetry, they're just kind of related by this 90-degree rotation. So 22.5 plus 90 will give me that kind of degree right there. So if I want to find out my principal stress state now, all I do is just do T stress lin flash dot theta goes to 22.5, and that's it. So these are my principal stresses. Let's go ahead and double check it. This is, again, pretty much 0, but let's go ahead and double check it. These were our sig 1s and sig 2s. So 7 point there, 2.4, again, approximately there, and we are good to go. So fantastic. So we've kind of matched, again, what we saw previously with our other solutions looking at kind of these problems right here. So we can with linear algebra, very easily, again, it's very, very straightforward, very simple to kind of rotate. And again, we could rotate in real space. We don't have to kind of think about these 2 theta rotation values, but you could also do more complex problems where now if I say, okay, from your principal stress state, give me a rotation that is 15 degrees clockwise from your principal stress state. Well, I would just do 2 theta, or actually this is just, my principal stress state. If I'm going clockwise now, it's going to be, again, minus, because I'm assuming, clockwise is my negative kind of value, minus 15 degrees is just this. There it is. If I asked you a counterclockwise rotation of 60, it'd just be not equal, plus 6. So my principal stress state plus 60 degrees. And et cetera, et cetera, et cetera. So I love the linear algebra approach, again, but it might be a good idea just to kind of conceptualize and get this idea of like, okay, the first sign of this rotation. So to make sure that you're working with the correct signs, draw out the Mohr circle, do the first rotation, get your principal stress state, and then use this linear algebra approach, and you just add. And again, you can stay in real space here as opposed to thinking about 2 theta and then going back to theta and back and forth, where it could give you some issues. So we're going to do another example problem pretty quickly here in the next day or so, or actually in the next video. Hopefully that'll help you basically work out and deal with some of these other problems. All right, thanks. I'll see you all next time. Have a good one. Bye.